In this video, I'd like to talk about one of the most standard pathfinding algorithms used in game development today. This algorithm is called A star. Also sometimes written like this, A with an asterisk. Now, A star combines the best of the previous algorithms that we've discussed. So we've talked about a breadth-first search, we've talked about a heuristic search, we've talked about Dijkstra's algorithm, which all have their own benefits, they're all pros and cons. A star aims to provide the benefits of all of them. Let's run through a quick overview, a quick example. Say we have a graph that looks something like this. Now, one thing with heuristic search is that heuristic search, because of that heuristic function, it allows us to more quickly traverse from a start node to an end node along a more direct path, right? It's sort of like an optimization to our function, right? We explore fewer nodes to come up with a same or similar optimal path. The benefits of Dijkstra's algorithm is it allows us to associate weights with each, or costs with each of the edges here. A star allows us to do both. And it does that by combining the best of both a heuristic search along with the benefits of Dijkstra's search algorithm. So let's do a couple things first. First, let's associate some weights with these various connections here. These represent how challenging or difficult it is to traverse along each of these edges. In a video game, we may increase or decrease these weights as the game is running as a way to represent areas that are harder or easier for our AI to traverse through. It may be something along the lines of the weights around this node are being increased because there's a grenade about to go off right there, or there are enemies closer to this area. Or maybe this is just more difficult terrain. This is some slanted slopes, or something is on fire over here. We want our AI to avoid this, but it could still move through it if it really needed to. We could also lower some of these weights based on benefits. There's a health potion over here, so we're going to lower the weights around it. It sort of encourages our AI to move towards those positions. One way that you could frequently use these weights and use these values is you could raise and lower them based on the obstacles in the world, or where friendly NPCs are, or friendly AI. There's a lot of flexibility here. As an AI developer, these are all the things that you should be considering. And I might add, one of the reasons why an off-the-shelf A-star algorithm or off-the-shelf pathfinding library is typically not the best answer for every single video game. So going back to our data structures, the frontier, or the nodes we need to explore next in our search algorithm, this is a reoccurring data structure. We used it in our breadth-first search, we used it in Dijkstra's and a heuristic search. This is still going to be a priority queue, which means that we're going to add elements in here, we're going to add nodes in here, and we're going to associate priorities with them. Now, with A star, we're going to calculate the priority in which we are going to explore frontiers using two values. We're going to use a heuristic function based on the distance to the goal, and we're also going to combine it with the weight of the nodes here, or the weight of the connections along these paths. So let's do some real quick examples. In this example, we're going to use this as our start node and this as our goal node. And as I go through this, I'll label the nodes. So our start node, node 1, is going to be the first thing added to our frontier. We need to give a weight associated with it, or a value for our priority queue, but in reality, it doesn't really matter, because really this is just the node that sort of kicks off the entire process. So we're going to look at the next node in the frontier, which is going to be node 1. When we go to process node 1, we're going to add nodes 2 and 3, as those are the only nodes connected to node 1. When we do this, we're going to add the values. We're going to add those nodes into the frontier, and the values that we're going to use for their priorities are going to be equal to the total cost to traverse that node plus a heuristic on how far they are from the goal. In this example, 2 would have a value of 1 plus this distance if we're going to use the standard heuristic function. If a standard heuristic function of just the distance from the target node to the goal node, right? And let's say this is a number of, 8, which means that this is going to have a total value in our priority queue as 9, right? 1 for the cost, and then 8 for the distance here. The next one here, this node 3, this is going to have a total cost of a connection weight of 3 plus a distance here, and we'll say this distance is half of what that other one is. We'll say this is a distance of 4, which means that this is going to have a total cost of 7. In this case, the next thing that's going to happen is A star will evaluate this node 3 next, because it is the one that has the lowest priority here. It's going to process node 3, and it's going to add this goal, right? We'll say this is node 4 into it, and then it's also going to add this one, 5. Now, node 3 took a total cost to get here of 3, so it's going to add 3 plus 4 when it goes to add node 4, right? So node 4 ends up being the cost it took to get to the previous node, 3, plus the cost it takes to get to this node, 4, plus the distance from the goal, this new node, to the goal, which in this case is going to be 0. So this is going to have a total cost of 7. Over here, this is going to add node 5 as a total cost of 3, plus the 1, plus this distance here. We'll say this is a distance of 5. So that would be another node of size 9, right? In this example, A star would now process this goal node here, node 4, as our goal, and we would be done. This guarantees to find the shortest path along this route. Let's do another example. In this example, though, I'm going to replace this node, this connection weight, from 4, and I'm going to increase it. I'm going to change it to a value of, let's go with 7. Now, for us as humans, just looking at this thing, we could pretty easily see that 7 plus 3, the path here from 1 to 3 to 4 to get to our goal, is actually greater than this path over here, going 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Let's see how A star behaves in a case like this. I'll go ahead and number those other nodes now before we get to them. So we have nodes 1, 2, 3, 4, 5. This will be nodes 6, 7, 8, and 9. All right, let's start. Node 1. 1, I put in here with a value of 0. It's our first node. So we're going to process it. I'll take node out. All right, node 2. 2, we're going to add in here as a value of 1. That's how much it costs to get there so far, plus this distance. We'll say this distance is 8. So this is going to go in with a total value of 9. 3 is going to be added to our frontier with a total cost of 3 plus this distance. We'll say it's 4. So this goes in with a 7. All right. So here's our 2 nodes, 1, 2, and 3. They've all been added. So now we're going to process the next nodes. We're going to process 2. 2 came in here, and we came here through 1, so it's had a total cost of 1 so far to get there. The next nodes that we'll process is 6. 6 will go in here with a value of 2, plus whatever this distance is. Let's call it 9. So now 6 is in there with a value of 11. So 2, let's see. So 6 just went in there with a value of 11. Then we're going to explore 3. We're going to see what happens there. 3 is previously in there with a value of 7, which was this 3 plus another 4 for the distance. The 4 is going to remain the same, the distance between 3 and the goal. But now we're going to put it in there with a value of 2, right? Because it only costs 2 to go this way. So one of the benefits of A star is it finds shortcuts in the same way that Dijkstra's algorithm does. This node 3 will now get added back into our frontier with a total value of 4, the distance, plus 2, which is how much it took to get here by way of node 2. So let's eliminate this node 3, and let's replace it with a value of 6, which is the 4 distance plus the 2 it took to get here. The next node for us to explore. The next node for us to explore is node 3. Node 3 will be eliminated. 3, it took us 2 to get here. Took us 2 to get here by way of node 9. So 2 plus 7 to get to node 4. Node 4 being here with a value of 9. Node 5. 5 will be in here with a value of 1, 2, 3, plus the total distance to get there. Let's say it's 5. Total distance of 5. Now in this case, the next thing that would happen is that we would process node 5, which is our node down here. There'd be nothing left for us to add off of node 5. And then we'd process node 4. which is ultimately our goal node. So we've discovered a goal. And actually, this is calculated that the best path is actually 1, 3. I'm sorry, it goes 1, 2, 3, 4 again. One of the issues that we have with this setup here, this example that I'm going through, where it may look obvious that this path around this outer edge is a lower total cost, is that actually my estimates for distances between these nodes is off, which is an interesting point here with A*. When your node weights are in the same value as your heuristic function, and by the way, what I mean by that is when you're using a heuristic function that uses distances between two nodes, right, as your estimate, plus you use node weights which are also equal to your distances between those two nodes, then A* will always guarantee to find the best path in a more optimal way than Dijkstra's or heuristic search. However, if the weights of your nodes like this, or the weights of your edges like this, where I'm just arbitrarily assigning them values, are not in the same value, or not like they don't match up with the distances with your heuristic, then is not guaranteed to find the same values. This is why sometimes you might actually see multiple weights associated with this pathfinding system. You may find that these weights are artificially increased or decreased and is not based on distance. With an example where we're using real distance values for each of the edges, which represent the distance between 6 to 7, the distance between 7 to 8, so on and so forth, and our heuristic is also based on the distances, A* will always find the optimal path. For our example here, and with our game, the field that we are going for, A* gives us back that our AI should move from 1, 2, 3, and 4.